Welcome back to Coffeesodes. You're joining us for episode 23, where we brew up a deep dive into the research you sent our way. If you want to follow along with us, check out the episode description for the source material. Today, we're exploring the fascinating world of sustainable energy storage. And it looks like you're particularly interested in how biomass-derived carbons, or BDCs, can be used to build better supercapacitors. I'm Josh, ready to get charged up about this.
And I'm Kelly, excited to unpack this research with you. Let's start with the basics. What exactly are supercapacitors, and why are researchers buzzing about their potential in the renewable energy landscape?
Yeah, what are they? Like, how do they even work?
Supercapacitors are energy storage devices, but unlike your typical battery, they store energy electrostatically on the surface of a material instead of chemically. This gives them some unique advantages. They can charge and discharge incredibly fast, tolerate hundreds of thousands or even millions of charge cycles, and deliver a powerful burst of energy when needed.
Oh, wow. Yeah. So are they like the capacitors that I learned about in physics in high school, or is that a totally different thing?
They are related to traditional capacitors, but supercapacitors take things to a whole new level. Think of it this way. Imagine meeting a quick burst of energy, like turning on a flashlight. A battery would be like a slow, steady stream, while a supercapacitor is a powerful instant jolt.
So like a battery is like a marathon runner.
Yeah.
And a supercapacitor is like a sprinter. That's a great analogy. So what makes them so important for renewables? I can kind of see how that quick burst of energy might be useful, but I guess I'm not seeing the big picture.
Well, think about solar and wind power. They're fantastic clean energy sources, but their output can fluctuate depending on the weather. Supercapacitors can act as a buffer, quickly absorbing excess energy when the sun is shining or the wind is blowing, and then releasing it when needed, smoothing out the supply, and making these renewable sources more reliable.
So it's all about like balancing out the grid, making sure there's always enough power available, even when the sun isn't shining or the wind isn't blowing.
That's a great way to put it.
That makes a lot of sense. So where does biomass fit into all of this? What makes BDCs such a promising material for supercapacitors? Isn't all carbon like the same?
It all comes down to sustainability and performance. BDCs are derived from organic matter. Think plant waste, agricultural residues, even things like nutshells, which makes them a renewable and abundant resource.
Okay, so like we're not digging up more coal or anything. We're using stuff that's already out there.
Exactly. And it's not just a greener alternative. They actually have structural properties that make them incredibly effective for supercapacitors.
Okay, now you've got my attention. What kind of properties are we talking about? The research mentions terms like high surface area and porosity, but I'm not sure I fully grasp their significance.
Imagine a sponge. The more holes it has and the bigger those holes are, the more water it can soak up, right? Well, in a supercapacitor, those holes are pores in the carbon material, and the water is the ions carrying the electrical charge. BDCs, with their unique structure, can have incredibly high surface area and porosity, allowing them to store a lot more charge compared to traditional carbon materials.
So it's not just about using a renewable source. It's about using a material that's inherently well-suited for the job.
Exactly. And there's another layer of complexity: heteroatom doping. This is where researchers intentionally introduce elements like nitrogen, sulfur, or phosphorus into the carbon structure.
Heteroatom doping, that sounds pretty high-tech.
It is, but it's also a bit like adding a pinch of spice to a recipe. It can dramatically enhance the electrical properties of the BDC, making it an even better conductor.
So BDCs aren't just a replacement, they're an upgrade. This is fascinating. Now, the research you sent over dives into specific types of supercapacitors called metal-ion hybrid supercapacitors, or MIHSCs. Can you tell us more about these?
MIHSCs combine the high power output of a supercapacitor with the energy storage capacity of a battery. The research focuses on several types: zinc ion, sodium ion, aluminum ion, and potassium ion, each with its own potential benefits. Zinc, for instance, is abundant and relatively inexpensive, making zinc-ion systems a very attractive option from a sustainability standpoint.
So is that the most common type being researched? Or are they all kind of neck and neck?
It's hard to say which one is winning at this point. They're all being actively researched, and each has its own strengths and weaknesses.
What about the other types? Are there any specific advantages that make them stand out?
Sodium-ion technology benefits from the wide availability of sodium and shares similarities with existing lithium-ion technology, which could make the transition smoother. Aluminum is lightweight with a high theoretical energy density. making aluminum ion systems interesting for applications where weight is a major factor.
What about potassium?
Potassium ions are larger than lithium or sodium ions. This size difference can actually facilitate faster ion transport, leading to higher power output. Researchers are still exploring the full potential of each type, but it's clear that MIHSCs offer a diverse range of options for tailoring supercapacitors to specific applications.
This is already giving me a much clearer picture of the landscape. I'm eager to dive into some specific examples of how these BDCs are being used in real-world applications. But before we do that, can you tell us a bit more about why researchers are so interested in these different types of MIHSCs? What are some of the unique challenges and opportunities they present?
That's a great question, and it gets to the heart of why this research is so exciting. Each type of MIHSC comes with its own set of advantages and challenges, making the choice of metal ion a crucial factor in determining the overall performance and application of the supercapacitor. For instance, zinc ion systems, while attractive for their sustainability and cost-effectiveness, are currently limited in their energy density compared to lithium-ion batteries. Sodium-ion systems, on the other hand, benefit from the abundance and low cost of sodium, but they face challenges in terms of achieving long cycle life and high rate capability.
Got it. What about potassium?
Potassium ion systems, while offering the potential for high energy density and fast ion transport, face hurdles in terms of achieving stable cycling performance. Researchers are exploring electrode architectures and electrolyte formulations to stabilize the potassium ions and enhance the overall performance of these systems.
So it's a balancing act,
Yeah.
weighing the pros and cons of each metal ion and tailoring the materials and designs to meet specific application requirements.
Precisely. And that's what makes this field so dynamic and exciting. It's a constant push to innovate, to find new materials and strategies to overcome these challenges and unlock the full potential of MIHSCs for a wide range of applications, from portable electronics to electric vehicles to grid-scale energy storage.
This is all incredibly interesting. It's like a choose-your-own-adventure book for energy storage.
I love that analogy. And it's a reminder that there's no one-size-fits-all solution in the world of energy storage. The beauty of MIHSCs lies in their versatility and adaptability, allowing researchers to tailor their designs to meet specific needs and create a truly diverse and sustainable energy future.
I'm definitely feeling more energized and informed now.
Okay.
I'm eager to dive into some of the specific examples of how researchers are using BDCs to create these high-performing MIHSCs. But before we do that, I have one more question. We've talked a lot about the potential benefits of BDCs, but are there any drawbacks or challenges associated with using them in supercapacitors?
That's an important question, and it's crucial to acknowledge that no material is without its limitations. BDCs, while incredibly promising, do present some challenges.
Oh, okay.
One of the key challenges lies in achieving consistency and control over the properties of BDCs. Remember how we talked about the importance of high surface area, porosity, and heteroatom doping? Well, getting these parameters just right and doing it reliably every time can be tricky.
Why is that?
The properties of BDCs are heavily influenced by the source material and the processing methods used. Different types of biomass have different compositions and structures, which can affect the final properties of the derived carbon. Even subtle variations in processing parameters, like temperature or heating time, can lead to significant changes in the material's characteristics.
So it's like baking. Sometimes the cake rises perfectly, and sometimes it falls flat. Makes sense. What about the cost of production? Are BDCs a cost-effective alternative to traditional carbon materials?
That's another key consideration. While biomass itself is generally abundant and inexpensive, the processing and purification steps involved in converting it to high-quality BDCs can add to the overall cost.
So it's not just about finding the right recipe. It's about scaling up production in a way that's both cost-effective and environmentally friendly.
Absolutely. Sustainability isn't just about using renewable resources. It's about creating a circular economy where materials are used efficiently, waste is minimized, and the entire production process is aligned with environmental principles.
That makes perfect sense. So it sounds like while BDCs hold immense promise, there's still work to be done to overcome these challenges and unlock their full potential.
Precisely. But the research is moving at an incredible pace, and there's a growing sense of excitement and optimism about the future of BDCs and energy storage.
It's amazing to see how research is merging sustainability, innovation, and cutting-edge science to create a better future. I'm eager to dive into some of the specific examples of how researchers are using BDCs to create these high-performing MIHSCs. But before we get to those, maybe we can take a quick break to refill our coffee cups and let all this information sink in.
That sounds like a great idea. We'll be back in a flash to explore the exciting world of BDC applications in MIHSCs. Stay tuned.
All right, we're back with our coffees refilled and ready to dive into some specific examples of how researchers are putting BDCs to work in these metal-ion hybrid supercapacitors. I'm excited to see what researchers have been cooking up in the lab. The paper you sent is packed with fascinating case studies showcasing the versatility of BDCs.
Yeah, it's really cool stuff.
One study that really caught my eye involved using eggplant waste to create a zinc-ion hybrid supercapacitor. It sounds almost too good to be true. Taking something that would normally be discarded and turning it into a key component for sustainable energy storage.
It really highlights the ingenuity of researchers in this field. They took eggplant, a food that's readily available and often generates a significant amount of waste, and transformed it into a porous carbon material through a process called pyrolysis.
Pyrolysis. That sounds intense.
It's essentially heating the material in the absence of oxygen. This breaks down the organic matter and leaves behind a carbon-rich residue with a highly porous structure, perfect for creating those sponge-like electrodes we were talking about earlier.
Oh, right, yeah.
Yeah.
And how did this eggplant-derived carbon perform in the supercapacitor?
It exceeded expectations. The researchers found that the eggplant-derived carbon exhibited a remarkably high surface area, which translated to a significant boost in energy density compared to traditional carbon materials. Plus, it demonstrated excellent cycling stability, meaning it could be charged and discharged repeatedly without significant loss in performance.
That's amazing. I'm starting to see eggplant in a whole new light. Are there any other examples of researchers using food waste to create BDCs?
Absolutely. The research paper mentions several studies utilizing various food wastes, like banana peels, rice husks, and even coffee grounds, to create high-performing BDCs. Each type of biomass brings its own unique characteristics to the table, influencing the properties of the final carbon material.
So it's like a culinary adventure for sustainable energy storage.
I love that analogy.
What other sources of biomass are researchers exploring for BDCs?
Agricultural residues like corn stalks and sugarcane bagasse, forestry byproducts like sawdust and wood chips, and even algae and seaweed.
Algae and seaweed, that's fascinating. What makes them attractive sources for BDCs?
Algae and seaweed grow rapidly and absorb carbon dioxide from the atmosphere, making them incredibly sustainable resources. Plus, they can be cultivated in a variety of environments, including saltwater, freshwater, and even wastewater, reducing the need for land and freshwater resources.
It sounds like a win-win for both sustainability and performance. Are there any particular properties of algae and seaweed-derived BDCs that make them stand out?
Algae and seaweed are naturally rich in elements like nitrogen and sulfur, which, as we discussed earlier, can enhance the electrical conductivity of BDCs and boost their performance in supercapacitors.
So it's like nature has already done some of the heteroatom doping for us.
Exactly. It's a beautiful example of how researchers are harnessing nature's ingenuity to create cutting-edge technologies.
The diversity of biomass sources is really impressive. What are some of the most innovative techniques researchers are using to synthesize and process BDCs? The paper mentions a few terms I'm not familiar with, like activation and templating.
Those are excellent questions, and they highlight some of the key strategies researchers are employing to create high-performing BDCs. Activation, for instance, is a process used to enhance the porosity and surface area of carbon materials.
How does activation work?
There are different methods, but one common approach involves treating the carbon material with high temperatures in the presence of activating agents, like steam or carbon dioxide. This creates a network of pores throughout the material, increasing its surface area and making it more effective for storing ions.
And what about templating? What's that all about?
Templating is a technique used to create BDCs with specific and controlled structures. It involves using a template material, like silica or zeolite, to guide the formation of the carbon structure.
So it's like creating a mold for the BDC to grow in.
Exactly. The template provides a framework for the carbon to form around, resulting in a material with a highly ordered and porous structure. Once the carbon is formed, the template is removed, leaving behind a network of interconnected pores.
That sounds incredibly precise. What are the advantages of using templating to synthesize BDCs?
Templating allows researchers to create BDCs with tailored properties, such as pore size, pore distribution, and surface area. This level of control is crucial for optimizing the performance of BDCs in specific applications.
It's like designing the perfect BDC architecture for each energy storage challenge.
Precisely. And that's the beauty of this research.
What are some of the key obstacles researchers need to overcome to make BDC-based supercapacitors a commercial reality?
One of the major challenges is scalability. Many of the techniques used to synthesize and process BDCs in the lab are not easily scalable to industrial levels.
So it's one thing to create a high-performing BDC in a small batch, but quite another to produce it in the quantities needed for widespread commercialization. And what about cost? We talked earlier about the cost of processing biomass into BDCs. Is that still a major barrier to commercialization?
Cost is always a critical factor, especially when it comes to competing with established technologies. While biomass itself is generally inexpensive, the processing steps can add to the overall cost. Researchers are developing more efficient processing techniques, exploring ways to utilize waste streams from other industries as biomass sources, and investigating alternative activation and templating methods that are more cost-effective.
So it's a multifaceted approach, tackling costs from every angle. While BDCs themselves are renewable and abundant, it's crucial to ensure that the entire production process, from biomass sourcing to BDC synthesis to device manufacturing, is environmentally responsible.
Right, sustainability is about more than just the materials, it's about the whole process.
So it's not just about using a green material, but about creating a truly green technology from start to finish.
Absolutely. This includes minimizing the use of hazardous chemicals, reducing energy consumption, and ensuring that waste streams are managed responsibly.
This deep dive into the world of BDCs has been incredibly eye-opening. I'm feeling a mix of awe at the ingenuity of researchers and optimism about the potential of these technologies to create a more sustainable future. And to our listeners, thanks for joining us on this deep dive into the world of BDCs and MIHSCs. We'll see you next time on Coffeesodes.